these things that are going on. So the first thing first, we have on Thursday this North American qualifier. Yes, so here it is, ICP. So it's the website is eventually going to be naq20.caddis.com, and you should be able to once you have. Actually, you might be able to do that right now. That if you log in. So I'm already logged in and I'm not part of the competitor. But if you log in with the email that you use um, to register your ICPC account, it should say that you are a competitor. Okay. So you might want to just check to make sure everything's fine. So this is occurring this Thursday from 6 p.m. to 9 p.m. Because this is not an official contest, if you want to, if you need help with anything, you can always ask on Discord, and tag me so I get buzzed and I will look at it. I have not seen the problems myself. I have no idea what the problems are, so I can't tell. I might be just as clueless as you are, depending on what you're asking me. Okay, so that's that one. And then the regional, it's going to be March 6th. It's probably going to be 10 to 3. That's our usual time, but the official time has not been really announced yet. So one thing that I want to make sure that everybody get familiar with is if you go to my GitHub, so there's this code library. This is a public repository, okay? So anybody can access it, and that hits all my all the University of Lethbridge Programming Contest Codebook. You want to concentrate, well, you can look at the index, and that tells you all the things that are in here. So you might want to just scan through it and see, you know, what you have. Some of the things maybe you have seen. Maybe you have seen breadth first search in your class or Dijkstra's algorithm. Some of them maybe you have never heard of. Right? Hungarian, you probably have no idea what this is about. Don't worry about the ones that you don't have any idea what it is about. Concentrate on the ones that you know, and just scan through it just to see how to use it. Okay, make sure that you know roughly what's in there. So if there's a problem that can make use of some of these algorithms, all you have to do is go to there and then copy, right? So if you go to one of these things, so for example, distance line. So this just says that this routine computes the shortest distance from a point to a line, i.e. the distance from a point to its orthogonal projection onto the line works even if the projection is not on the line. You have the structure xy, which is a point, and then computes the distance from from C to the line defined by A, B. So what does that mean, right? So it means that, oh, I forgot to turn on my writing pad. Is it on? Okay. So it means that, why is it not writing?
Howard, do you know you have 2 different cameras on you right now?
Oh, okay. Let me stop that. Okay. Just so that you, okay, here it is. So you have a line defined by A and B, and then you have some point C, and the distance is basically, if you look at the perpendicular projection, this is the distance. This is what it computes. Okay. Anyway, this is just one example. There are lots of different things here. And if you go and look at the index, it's sort of classified into different sections, right? So there's something about arithmetic. So how to compute binomial coefficients, for example, Chinese remainder theorem. For those of you that are number theory, you might have seen that. Linear Diophantine equations that you might have learned, you might be learning in number theory. This actually is the super duper version. It doesn't work for just one single equation like you learn in number theory. It actually works for system of Diophantine equations. Euclidean algorithm, something called Euler phi. Again, if you know number theory, you might know what that is, etc. And then there are things about geometry. Area of a polygon. If you have 3 points, whether it's clockwise or counterclockwise, it turns out this is really useful if you know geometry. Computers, if you're given 3 non-collinear points, you can compute a unique circle that goes through it, and so on and so forth. Intersecting lines, finding out if a point is inside a polygon, etc. There are graph algorithms, different shortest path, and other things. So if you're in 3620, you would have seen some of this. Minimum spanning tree, network flow, etc. Data structures, we haven't really spent much time talking about these things, at least on these sessions, so maybe I will skip that. These are more advanced. And then there's some miscellaneous things. And anyway, so have a look, and whatever you don't know, but if you're curious about something but you don't know what it is, either send me a note or look it up somewhere, but feel free to send me a note, and that's probably the easiest way. Okay, so make sure that you know this, and I guess, well, okay, for our top team, I don't have to tell you to look into this ICPC folder to figure out what's in there. There are also some, I don't know how useful it is, but we used to print this out and bring it in when we only allowed paper documentation. This is what they call a computer science cheat sheet. All of these identities that may or may not be useful. Probably it's not very useful for most part. This is sometimes useful. Trigonometry and cosine laws, sine law, and all that stuff. If you don't remember them, blah blah blah. And then there's what else? There's something called math hints, which are some formulas that you might. So more geometry, trigonometry, and volume and surface area of stuff. Okay, so anyway, there's stuff here. And also remember that in this contest, it's very unusual because we're doing it online. So you're allowed to use any material that you can find online, provided that it is not behind some private, whether it's subscription or paywall or some other locked account. So this is, my repository is open to public, anybody can use it. So that's why it's okay. And whatever else you can find online, as long as it's something that anybody can find online, it's okay. And the other thing is you're not allowed to post something on a forum or chat with somebody outside of the contest. So like you can use Geeks for Gits, for example. I actually don't know. I have absolutely no idea what Geeks for Geeks are, so I guess I'm not geek enough. So what exactly is here?
This was my professor for 3620, pretty much.
Okay. So I think as long as you can, if it's something that you can click on a page and it gives you something, yeah, you can use any of that. But if there's like, is there a forum or anything?
I think there is, but I wouldn't be using it during a contest. I just,
Yeah.
when you Google algorithms, commonly this site comes up. It's pretty good.
Okay, so as long as you don't end up using a forum or chats or something, it's fine. Okay.
And for the online rule, is that just for this Thursday contest, or is that for the
No,
one in
okay.
March?
This Thursday, nobody cares because there's no official, no official reward for doing well or poorly. Okay. So, but for the regional, this is March 6th. That has implication because the top 8 teams from the regional will then go on to this super regional, which is whatever they call it, division contest, which is going to be all the top teams from the west side of North America. And then after that, there'll be a North American final. So, so for the regional, there's going to be more rules. For one on Thursday, nobody cares.
Okay.
You can even ask me for help if that is somehow helpful. Okay, because it's, for me, I'm just treating that like a practice. Okay.
Yep, sounds good.
Okay, so anyway, make sure that you are familiar with my code library. It's here. I think I have this on Discord, the link. And then, of course, this that you have, some of you have been looking at as well, my solutions to this, to whatever I've done, it's also publicly available. So just like many other people post their programming contest solutions online, this is all my solutions to problems that I already solved, right? But of course, the problems that you see will not be the same, right? Okay, so that's kind of the logistics of the regional, and then top 8 team will go. Now, one more thing, they have not completely decided on how they want to monitor the team. So what do I mean by that? If you're trying to compete, you have 3 people, obviously you're not going to be at the same place. So you're going to have three computers, one each. You know, what if you have, I don't know, another tablet or something to open and have one screen on this and that? Well, we're not going to be able to check. But how do you communicate, right? Are you going to use Zoom? Are you going to use Discord? Are you going to use whatever else? That is not finalized yet. We don't know. And whether the contest organizers want to insist on every group, insist on them being able to get into any group chat for any team, I don't know yet. They're talking about it, but it's really organizational nightmare. There's no way I want to sit into 10 different teams, private meeting. There's no way I can keep track of things. So anyway, I don't know where that will be at. But other than that, for the regional contest, it is basically doing it on your own computer. Okay, and then chat with each other somehow. All right. Okay, so those are the, I guess, what do you say, the logistical things. So I'm going to start talking about the problems from last week, last Saturday. Okay, so this is a real regional contest from 2018 in Singapore. And Singapore is a pretty strong region. And some of the problems are pretty hard. And if you look at the standings, the people that are on top are people that are, you know, ex-world finalists. Richard Peng is actually an ex-world finalist from Waterloo and now actually a full faculty member somewhere. So he's not even a contestant really. And then you keep going down, and then our closest competitor would be Calgary here, and they solved 6 problems. And then we have the squids and the octopus. That's Joseph, and he did 5, although he probably could have done more because he's seen these problems before when we were practicing for the North American Regional last year. Sorry, North American, whatever it's called, North American Championship. That's what it was called officially. And Dustin did 3, and then the other ones did 1, I believe. Okay, so we will, well, first, I'm going to somehow try to mute my daughter downstairs. Can you actually hear her? I don't know. Let me see if I can.
A little bit, but she's not like loud or disruptive.
Okay, let me see if I can send a command to mute her. That probably doesn't work. What I mean is I'm going to tell my wife to see if we can quiet her down. Okay. Anyway, all right. So there are these problems, right? So if you look at the number of problems, number of times the problem is solved, so clearly free food is the easiest one, 99. 68. Sorry, the next one is this SG coin, 72. And then non-prime factor is 68. Now, there's something a little bit strange here, perhaps. Free food has 99 solutions, and the success rate is 73%, which is not bad. SG coin has a lot of solutions and half right. But non-prime factors, even though it has a lot of people solving it, the average number of tries it takes to get it is pretty high. Like an average tries is 4.26, an average tries to get is 3.41, and only 18% of the submissions are correct. So maybe something is a little bit weird here. And then which other ones? Which one is the next? They're hoppers. Hoppers, nobody in our group actually did or tried, as far as I can tell. But it seems like it's not that bad, especially if you try it. 48% of people got it. So I guess it's one of those things that if you didn't know what to do, you wouldn't randomly try a problem. And then which other problem did I say I was going to look at maybe? Conveyor belts and bitwise if we get to it. Okay, so let's get to it. Free food. Okay, let me blow it up a little bit so it's easier to see. Okay, so the idea is that you have a bunch of events, n of them, and it's at most, I'm going to try this, n is at most 100. I don't know if I like this fake laser pointer. Okay, let's not do that. Okay, so 100, and each of these events starts from day S to day T. And free food is served for that event every day from S to T inclusive. Your task is, in this problem is to find out how many days there are in which free food is served by at least one event. So then they give you an example. There's 3 events. The first one is 10 to 14. And then the second one is 13 to 17. I'll write it like this. And then 25 to 26. Why do I write it like this? Because there's an overlap of 13 and 14 here. So on those days you get free food twice, but that doesn't really matter. You only care about which days you have free food. So basically free food from 10 to 17. So that's 8 days. And then 2 more days here. So the total is 10. That's the answer. Okay, so basically you have a bunch of events. Every event has start and end time. Start and end time are always between 1 to 365. And then you want to know how many days it's served, you have free food. Okay, so I think most people, I don't know if that's completely true, but I think most people that tried eventually got it. And the idea is to realize that you have this 365. There's a very finite range of what you care about. So what am I going to do? I'm just going to have a Boolean array that's indexed from, well, I guess you always have to start indexing from 0, but it's indexed from 0 to 365, and initially set them all to false. Okay, so this just says, is there free food that day? And then every time you see an interval, they tell you what S to T is, so 10 to 14. You go to 10, you go to 14, and you write a loop that puts truths in those spots. Well, actually, I need 5. Okay. And then basically every time they give you something, you just write truths in that range. It doesn't matter if you overwrite things that it's already true. And then at the end, you just count how many truths there are. Okay. So every time the worst possible case is that you fill the whole array. So in the worst case, each interval, it takes you 365 steps to fill. Multiply that by 100 events. So that's, well, that's nothing. So you can just brute force it, really. So are there any questions? If there are no questions, then really it's just the question is how fast can you write this code? So here's my code. I'm using stl a lot, but it doesn't, you don't have to do that. So anyway, here's a Boolean array, 366, because I start from 0 and go to 365. So I don't know if there's any, if you're not careful, maybe you write to 365. But anyway, just make sure that it's 366. This sets everything to false. Because in C++, this set the first element to false, and then the rest of the elements that are not specified are initialized automatically to 0, which is also false. Okay, I read n, and then I loop through it n times, and then I say read s and t, and then I use this fill. Okay, so fill basically goes through an array, goes through a bunch of elements starting from s all the way to t. Okay, so in C++, the range that you specify, it's always one more than you need. So s to t, but the n has to be 1 past the end of the range that you want. So I'll go to t plus 1, and that fills this range, fill them all to true. And then at the end, I just count how many trues there are. So again, this is an stl function. If you don't like that, if you're not familiar with this, you can write a loop yourself to fill out the elements from s to t to true. If you don't know the count function, you can just loop through the array and just count. If there's a true, do a plus plus, right? So even if you don't know all these STL magic, you can still do it pretty quickly. Okay, any questions? This one is pretty straightforward. Okay, the next one is very scary. It looks very scary because the description is long and they give you this big chunk of code. And so what the hell is going on? So let's read this. Okay, so they say that there's a new cryptocurrency called SG Coin. Alice purchases an item and pays in SG Coin. The transaction is recorded blockchain. A blockchain is a chain of blocks, where each block contains a hash value of the previous block, a transaction string, a token, and the hash value of the new block, which is always a positive integer with 7 trailing zeros. So for example, you have the previous block, it's whatever this is, you don't know, but the previous block hash value is 14 with 7 zeros. So the next block, the previous hash is of course 14 with the same thing. You have some string, that tells you what happened, and then you have some funny token. And then if you stick these 3 things into a certain function, it will grind out a new number, which is 99 with 7 zeros after that. Okay. The token in the new block must be set to a number between 0 to 1 billion. Well, actually 1 billion minus 1, such that the hash value of the new block is positive and has 7 trailing zeros, like this. So if the token is blah, then the hash value is computed with this magic function h. What is this magic function h? We'll look at, because it's, oops, hang on, sorry, I hit the wrong place. So the magic function is given below. And then it says that there might be other valid values for token that also gives a hash that has 7 zeros, blah, blah, blah. And then it gives you some other big story, blah, blah, blah. Okay, and then there's this function in C++ and in Java. They're both the same thing, but in different language. So what are you going to do? You are going to try to, you're going to get the hash value of the last block, this one, the 14, what is it, 140 million. So 14 with 7 zeros. You have to construct 2 new blocks so that this block will give some hash value that's correct, and then the next block will give some hash value that's correct. So you have to produce a new chain. And for example, here, from this one, you can produce this one, which then changes to this one. And it says that if you compute the hash values, it's going to be these ones. Okay, so what's happening? Okay, this is a little bit tricky. So you have your block that has the 14. I'll just write 14 because I don't want to write the 7 zeros. This is the block that you have from the last one. This new block that you have to create, this is block A. You have to create 2 new blocks A and B so that the previous hash it's of course 14,000. Then you have to have some string. That's this Charlie pays to Eve thing. You have to produce that string. You have to produce a token so that the new hash value is also something, something, and then a bunch of zeros. And then this would then train to the next one. You have some string, you have some token, and then the hash, it's once again, I'll just write YY, and then 0, 0, 0, like this. So you have to be able to tell me the string and token for block A, so this is A, and this is string and token for B. Okay. Now, if this hash function is a black box, you're pretty much toast, because how are you going to try to generate anything if you don't know what this hash function does? So we have to go and see what this hash function does. Okay, so this hash function takes the previous hash, a string containing the transaction and the new token, and then return something. Okay, so the first thing to realize is that there's this mod, what is it, 1 billion plus 7. That's a very common one. So this is a very common prime that's used in a lot, 10 to the 9 plus 7. So I'll just write P. This is actually a prime, but it doesn't really matter for us whether there's a prime or not. Okay, so you start with V, and then every time, for every letter that you see in the string, you're going to multiply V by 31, and then add the character. Okay, and then mod this. So let's forget about this mod for now. What does this actually do? Well, you're going to start with the previous hash. Okay, so it's going to be a previous hash at the beginning. I'll just call it PH. And then the next times through, it'll be PH times 31 plus the first letter. And then the next times through, it'll be PH times 31 squared plus the first letter times 31 plus this one. And then the third 31 cubed plus T0, 31 squared plus T1 times 31 plus T0, and so on. Every time I process another character, not T0, T2. Every time I process another character, I'm multiplying everything by 31 and then add the next character. In other words, I'm kind of treating this as digits of a base 31 number. Kind of. Why do I say kind of? Because there's no guarantee that these numbers are between 0 to 30. Normally, if you have a base B number, the digits have to be between 0 and B minus 1. But there's no guarantee any of that. And in fact, it's likely not to be true. But anyway, that's kind of the idea. And then at the very, very end, where does the token come in? You take whatever that result is, multiply that by 7, and then plus the token. Okay, so that's what's happening. So now you have to somehow try to figure out a token and a string given previous hashes, so that the last bunch of numbers are zeros. That's the challenge. Okay. So how do we do this? Well, it turns out that actually whatever the previous hash is, I can just pick a really short string. You can pick whatever string you want. In fact, I think in my code, I just picked the string with a single letter A. I can grind through this first part, and out comes a value V. And I can then multiply V by 7. And then I need to add the token so that this is going to be something, something, followed by 7 zeros, mod P. Okay, that's what I need to do. So how do I accomplish this? Well, this is of course xx times 10 to the 7, right? So what I want is I want v this has to be equal to 0 mod 10 to the 7. Because when this number is divided by 10 to the 7, it becomes 0. So what do I do? I can compute v times 7 and call it the new v, doesn't matter, I call it w. Well, how do I do that? Well, whatever this is, let's imagine that this is, I don't know, 123. What do I need to add to get to 0? Well, it's how do I write this? Token is equals to minus 123, which I guess it's also congruent to 10 to the 7 minus 123 mod 10 to the 7. So basically what I'm saying is you compute everything according to the algorithm up to this part, and then you subtract it from 10 to the 7, and that's pretty much your answer for the token. And it doesn't matter what string you choose, you can always do this because you can always get your value here, and then you can always subtract it from 10 to the 7. So what I do in my code basically is they give you the previous hash value to start things off. Then I form this block A with the string A and the token computed in this manner. And then this would be the next hash value. And then I just repeat the whole thing with the next block. I use the same string again. I compute the same token, the token in the same way, and the next hash to make sure that everything is right. And that's it. So here's my code. Okay, so let's just do this. So I read in the hash values. Let me make it a little bit bigger. Maybe it's easier to see. This is the hash value from the previous block, and then I just pretend that the string is the single letter A, and this function computes the token, and this h function is exactly what I pasted from the problem statement. So that computes the next hash value, and then we do the same thing. I use the same string, I compute the token again, and actually this I don't even need to compute because I don't need the hash values of the last one, and then I just print that. So the magic is, how do I compute this token? Okay, the h function I can show you, but there's really nothing to see because it's exactly the same exactly the same thing as what's in the problem statement. Okay, so here it is. T. This basically does exactly this this for loop in the original h function. I didn't have to have this because I pass it in, so I don't have to assign it. So basically, this first part is just here. And then I multiply that by 7. And then I do it mod p because I am looking at things mod p. And then token. Okay, what did I do here? I did t minus u mod. Okay, so this u mod 10,000. Okay, did I lie to you about what I did? Okay, what am I not getting right? Okay, so let me just retrace my step here. Okay, so maybe I made a mistake here. So I have this u, that's my v times 7, plus token. I want this to be something times 10 to the 7 mod p. This is what I want. And so what do? I say, so I say token, it's of course u minus, I guess minus u plus x times 10 to 7 mod p. X, I don't know what x is. And then what am I trying to do? So of course, this minus u is the same thing as p minus u. And then I'm doing divide remainder of 10,000. Why am I doing remainder of 10,000? Oh, I mean one remainder of 10 million. Okay, what am I not getting right?
It has to end in enough zeros.
I have to end with enough zeros. So why am I getting hung up on here? I'm trying to figure out what it is that I'm not understanding or forgetting. Okay, u. So I'm doing this u mod whatever it is. So okay, so let's say if u it's, I don't know, 123. Okay, so u mod 123. So u mod this is of course still 123. P minus that would be 10 to the 9 plus 7 minus 123. So then if this is my token, and then I'm trying to add u, so if I try to add u, then this is going to disappear, and then I get 0. Okay. I am very confused. Why am I very confused? Joseph, help me.
I don't know if exactly we did the same thing, because if I remember my approach correctly, I also picked my hash explicitly to be a billion.
Okay.
And I don't know if you mentioned that you were doing that anywhere, because my code looks a little different.
Your code looks different, right? Well, there are different ways you can do this. I know that this is completely different from the solution slides that they posted. This is very different from what they do. Okay, so I know that this is right because it's accepted. The only question is, how do I recover the math that I did? So I say that, okay, so u times 7, it's here, mod p. So wait, my p, let me just make sure that my p is 10. Yeah, okay, it's this one. Okay, so I'm not hallucinating. The p is something else. Okay, so then if u is whatever it is, let's say this much, then I'm doing p minus u. Token is now p minus u, because when u is smaller than billion, 10 million, it doesn't matter, this mod. Okay, so then u plus token mod p, it's of course 0 because u plus token is just p. So so even if this is bigger than 10 million, let's say you have a bunch of other things. Okay, so let's try something else. let's say that you have something really big, 999, whatever, lots of nines. Then when you do the mod this, you'll end up with just, I guess, just a certain number of nines. 1, 2, 3, 4, just 7 nines. Whatever it is, let's say like this. And then token, it's always going to P minus this, P minus 999, like this. And then if you say U plus token, so U plus token could be a lot of nines, U can be many, many nines, plus token, it's going to be this minus this, and then plus a lot of nines, and then these nines, this one cancels out, and you end up with a bunch of zeros at the end, 7 zeros, and then when you mod the P, this will have the required number of zeros. Okay, so that's how that works. So you basically make sure that this last 7 digits is canceled. I guess that's what happens. Yeah. You want the token. So if U is something, whatever it is, followed by 7 digits, whatever this might be, 1, 2, 3, 4, 5, 6, 7, then U mod 10 million will be this part. And then when you say P minus this part, and then add it back to U, right? So this is P minus this part is effectively this part negative. So when you add the two together, you get U equals to P plus this part, but then this part cancels out and you get 0, 0, 0. Okay, that's how it goes. So when you mod P, then this disappears, and then you end up with 7 zeros at the end. Okay, I knew that this makes sense at some point. Okay, so, and then there's one final thing that I don't know if that was important. It's to make sure that, okay, what is this? Well, token is bigger than equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 billion, I add 10 million. Why did I do that? Is there a reason? Is there a range of what the token has to be? Token has to be a number between 0 and 1 billion, less than a billion. So if it's somehow bigger than a billion, then I have to adjust it. I think that's what happened. Wait, I'm in the wrong window. I'm trying to figure out which tab to tap. Okay, so this just, so I can bring it down, but I have to make sure that I always change things by something with 7 zeros in it to make sure that I don't screw things up. I guess that's how that goes. Okay, anyway, okay, that took a lot longer than I wanted to spend. But officially, there's a different solution. If you actually go to the website for this regional, it says something completely different. And what they say is that because you have 7 zeros at the end, there are actually only 99 different possible hash values. So because it can only, so it has to be 1 with 7 zeros, 2 with 7 zeros, all the way up to 99 with 7 zeros. And because there are only 99 of these, you can actually do some pre-computation about how you get these things and then try to match things up by looking up the table. I didn't actually follow that completely because I already solved the problem. I didn't really care. Anyway, so there are many solutions. That's the one that I did. Who else did it? Joseph, you did it. You said you did something else?
Yes, but I think it's very similar.
Similar to what I did?
Yeah.
Okay. And I think Dustin also solved the problem, but I don't know how he did it. Okay. All right, so that's much longer than what I thought I would be doing. Anyway, any questions? I did stumble through that one a little bit. Any questions about this one? Okay, so let's try the next one. Okay, so this one, I think a number of people try this and maybe didn't get it. So this is actually a really nice problem because there's not much to read. So you want to count the number of non-prime factors of an integer I, and the integers are, so for example, integer 100 has non-prime factors, 9 factors, 1, 2, 4, 5, 10, 20, 25, 50, 100. And the number of non-prime factors is 7. So you look at 1, 4, 10, 20, 25, 50, 100. You ignore 2 and 5. Okay. So when you have such a thing, when you're asking for prime factorization or computing factors, if you are going to be asked the question for a single number, there's not much you can do. You just have to basically divide. Try all the divisions. Try all the numbers from 1 up to the square root of the number, and then see if it divides. And then for each one, you have to decide whether it's prime or not. The problem, of course, is that you are going to be asked up to 3 million of these queries. And if you're going to do that all the time, it's going to be a problem. Now, also, the numbers that you're going to be asked for, it's going to be up to 2 million. Now, even if you don't know anything about number theory, you should be able to tell that if somebody wanted to ask you 3 million queries, but they can only ask you about 2 million different things, some of the questions will be repeated. Okay, right? If they want to ask you 3 things, but you only have two questions that you can ask, at least one question would have to be a duplicate. So immediately, even before you know, you try to figure out any number theory stuff, you should know that maybe you should remember some things that were asked so you don't have to recompute all the time. Because for sure, you're going to get asked something multiple times. Okay, but anyway, that's not the main technique here. The main technique here is to realize that you can only be asked questions up to 2 million. Okay, so there's a relatively small range. I mean, you might not think that a million is a small range, but even up to 10 million, you can still easily do this. Okay, so what are we going to do? Okay, so we're going to use a very common thing called a, did I spell SIF correctly? I never really remember if it's IE or EI. The SIF to figure out prime numbers. Now the SIF is usually used to figure out which numbers are prime. Okay, but we will start with that. Okay, so how does the SIF work? You have a Boolean array, and it's going to be indexed from 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, all the way up to whatever number that you are interested to know. So in this case, would be 2 million. Okay, this is a Boolean array. You don't actually care about 0 and 1 because you don't care if 0 and 1 are prime. It's the other numbers that you care about. Okay, so what do? We're just going to cross out this. Everything at the beginning would be true. So at the beginning, everything is true. So you just fill it like this. True means that it's prime. All right. So what are you going to do? You're going to do something like this. For int n equals to 2, n less than or equal to capital N, n plus plus. Okay, so I'm going to go through each one. If prime I, so if it's prime, then I need to do something. Otherwise, I don't do anything. Okay, let me put this down here. Okay, what am I going to do? I'm going to go for int k equals to 2 times n, k less than or equal to capital N, k plus equals n prime k equals to false. Okay, so what did I just do? So I'm going to loop through, I'm going to start at 2. 2 is still prime. So now I need to say, let's start at 2 times 2, so 4. This is not prime anymore. And every step, I'm going to jump by 2. So I'm going to mark 6, 8, 10. Every second one, I'm going to say it's not prime. So what am I doing? I'm basically saying all the multiples of 2, I know that they're not prime, right? Okay, so now I mark up all the multiples 2. So now I come back here, n is now 3. So n is now here. It's prime again, so I now go knock off all the multiples of 3. It's already 6 is already knocked off. 9. Well, let me write a few more. 12, 13, 14, 15, 16. So 15 is going to be knocked off and so on. Then I go to 4. 4 is not prime. I don't do anything. 5 is prime, so I go and knock off 10, 15, 20, and so on. 6 is not prime, I don't do anything. 7 is prime, so I got to go knock off 14, 21, etc. And so on. I keep going. And then eventually I would have an array so that anytime I have an x, it's an x because it was a multiple of somebody, multiple of a prime. Okay? Does that make sense? And if you do that, if you're going to do this, then how long does this take? Right? So here with this loop here, this is a double loop, I can figure out all the numbers from 2 to n, 2 to capital N, whether they're prime or not. But how long does this take? Well, this is a little bit tricky. I'm going to do it n steps. But the first time through, this loop executes n over 2 times. The next time through this loop, it executes n over 3 times because it marks up all the multiples of 3. I jump by 3. The next loop, it's n over 5. Well, I'm skipping the one that are not prime, right? And so on. So how much is that? Well, how much is that? I don't know if I want to go through this, but I'll just say it's n log n. If you want to know why, you have to use calculus and try to do kind of a integration of something. So, do I want to say anything? Sure, why not? So, if you have a graph, this is a x, y, and then you have y equals to 1 over wait, what am I drawing? 1 over x. That doesn't look like 1 over x. What am I drawing? Hang on. I'm kind of confused here. Let's try again. So this is n. You can think of n times 1/2 plus 1/3 plus 1 over 5th plus whatever. Okay, so 1 over x, it's more like this. Well, kind of, it's general shape like this. And then you're looking at 2, 3, 5, 7, etc. So 1/2 is here. So you can kind of draw a rectangle like this, right? And then if you sum these rectangles up, then of course it's going to be less than the area of this curve from, let's say, 1 to n of this curve. dx, right? And then you figure out the integral of this. What's the integral, right? It's basically, I'll just write log of x, right? And then revalidate n to 1. So basically, it's log x, so log n, but then it's n times log n. So that's how you get the n log n. So n log n is pretty reasonable, even for n being, let's say, tens of millions. So this will work pretty quickly to figure out which numbers are prime. Okay, so that's the CIF to quickly figure out all the numbers in a range that are prime. But that's not really what you're asked to do. Okay, you're asked to do something else. What are you asked to do? You're asked to do for each number in this range of, well, for some numbers, possibly all of them, you're asked to figure out how many non-prime factors there are. So what to do? Well, the first thing is, instead of using Boolean, instead of Boolean prime, let's say int factors, okay, the number of factors there are. And instead of using Boolean, let's say that these are integers and count how many factors there are. So at the beginning, let's just set them all to 0. Okay, I won't even write it. Just set them all to 0. And then we are going to do what? We're going to do something a little bit different because we want to count non-prime factors. Oh, wait, what the hell am I doing? This should be an n. Okay. So if it's not prime, then I'm going to mark off all the multiples. And this, we're not going to use the word prime anymore. We're going to use the word factors. Right, okay. So I'm still going to have the prime array somewhere else. So I still have to know whether the number is prime or not. But here, I'm going to do a plus plus. Okay, so what's happening? So all of these are prime, so nothing happens. Here, I know that it's not prime. So now, what am I going to do? Actually, I'm going to start from n. All the multiples of 4, I'm going to mark an extra factor. So 1 here, 1 here, 1 here, 1 here, and so on. So every multiple of 4, I'm going to remember that I have one more factor. Which one? 4. 5 is prime, so I don't do anything. 6 is not prime, so I remember 1. 12, I have the plus plus. 18, I would plus plus, and so on. 7 is prime, so I don't do anything. 8 is not prime, so I add all the multiples of 8, and so on. 9 is not prime, so I add the multiple, and so on and so forth. So basically, what I do is I run the CIF first time to figure out which numbers are prime, and then I run another kind of CIF-like thing, but this time I'm doing it on the non-primes. So if it's non-prime, then I'm going to go around and mark all of my multiples to say that I divide you, right? So I divide you, and then basically the factors of k will collect all the people that divide them that are not prime. And it doesn't you don't actually have to run this. So I said you run this loop with the CIF, what I wrote before, and then you run this loop again with this. You can actually, if you really want, fold the two loops together. You can actually run them all at the same time, I think. It should not be a problem. They should not interact with each other in some funny way. So let me see my solution. my solution? How come I can't find it? This one? Hang on. For some reason, it won't let me switch to that tab. I don't want conveyor belts. Okay, let me just close this because that's supposed to be the next one. Okay, so here it is. I have answer, which is all zeros, so that's my factors, and then the Boolean array that allows me to figure out if a number is prime. I initialize my number to be true, that the prime array to be true. I initialize the factors to be 1, I guess. I don't know why. Why did I initialize to be 1? Oh, because 1 divides all of it, of course. 1 divides everybody, and 1 is not prime. And then here, I basically do what I just told you. So this part is the CIF. So it just runs it and basically mark all the things that are prime or not. And at the same time, if it's not prime, then I go and mark up all my multiples. Okay. And then I do all of this computation at the beginning. And then I just, you tell me how many queries you have. For each query, you ask me what number you want to know, and I print out the answer of, I print out the answer just by looking it up because I computed them all. Okay, that's it. Now, I don't know how many of you might have seen things like this. Forget it. Don't worry about it. This is a way for C++ to speed up its I/O if I'm suspecting that my program might be slow because of reading and writing a lot of input and output. Then I put that in. But you actually don't need that for the regional. We make sure that the problems can be done without this. Okay, so don't worry about this line. Okay, so for those of you that are or have taken number theory, this is something that you should probably have seen, but maybe you haven't exactly implemented it before. Any questions about this? Okay.
This might be kind of a dumb question, but wouldn't you only have to go to 1 million if the biggest possible is 2 million? Because factors are only up to the square root of it.
Yeah, okay, so the answer is yes, you're right. Oops, what just happened? Oh, God. Firefox has just been updated in the background. Restart. Okay, I'm not going to swear on a recorded video. So what should I do? I don't want to restart, so let me just start a terminal so I can show you my code. Okay, so here's my code again. Let me make it higher. Okay, so you are completely right. Because if k is more than 1 million, then this step here, it's just going to be, this step is already going to be more than 2 million. So this loop will never execute. Okay, but what is needed, I guess, is here, because I set initialize this double k to be k, it will still execute one time. Okay, so what the issue is? The issue is if I have a number that is big, right? It's always divisible by 1 in itself. And if it's too big, right, because I start at k, then it will not get that second number by itself. So what I could have done is I could have gone to 1 million, like you say, but then I initialize this to 2 because the number, it's always divisible by itself except 1. Which number is not always divisible by 2 factors? Right, the number is always divisible by 1 in itself, that's true. But primes, if it's a prime, then it's not divisible by itself. Well, it's divisible by itself, but you don't want to count it because it's prime. But there's a non-prime that is not divisible by 2 factors? Can anybody tell me which one?
1.
1, exactly. Okay, so you can do this trick to say go to 1 million, set this to 2, but then you have to be careful about the prime. You have to be careful about 1. So I guess I just didn't bother being careful.
I think the smallest number they can give you is 3, though.
Is that true? I don't remember. Of course, I can't see it now because I closed the tab, and Firefox will refuse to let me open another tab until I restart. Okay, so if the number, okay, can I actually click on this? Would it let me? Ah, it would let me. Oh, the smallest number is 2. Okay, so you don't have to worry about 1. Okay, they're a little bit nice to you. Okay, any other questions? All right, this one I actually haven't done myself, but I'll talk about it anyway. I don't think anybody tried it. Problem B. I mean, not anybody in our group. D. Oh, I was wrong. Joseph did it, and that's it. Okay, so what is this problem? So you're part of an elite hacking group, blah, blah, blah. You have a new type of malware called a hoppers. It can operate in high security computer networks, but they can only propagate themselves in a very limited way. Okay, so you have a set of hosts, capital V, and direct links, E. Each direct link connects 2 different hosts, allowing them to communicate in both directions. So if they're telling you that you have an undirected graph, if a host is infected with a hopper, then it will propagate itself to all hosts W, where W is the set of hosts which are connected to any neighbor of U. Okay, this is a little bit convoluted. Okay, so let's read it again. A host U is infected, so maybe it helps to draw some picture. So you have a host U that's infected. So let's, I don't know, make it red or something. So it's infected. Okay, then what can you infect? It says that it will propagate itself to all hosts W, where W is a set of hosts which are connected to any neighbor of U. So you first have to think about the neighbors of U. So these are neighbors of U. And then things that are connected to neighbors of U. These are the ones that get infected. Oops, oh, wrong thing. These are the ones that get infected. So you're somehow not able to infect your immediate neighbors, but you are able to infect things that are 2 steps away. Now, what I draw, when you draw pictures like this, you always have to ask, did you mislead yourself with the way that you draw these pictures? Okay. So the way that I draw this, right, you infect, of course, U is infected, you infect everybody 2 steps away. But things that are 1 step away can also be infected, because this one, even though you can't be infected directly like this, it can be infected in 2 steps like this. And similarly, this one is also infected. So here, even though these 2 technically have distance 1, they can be infected. Okay, so whenever you draw pictures is a really good way to visualize things, but you always have to ask yourself, are you sure that you didn't mislead yourself with your picture? Okay, now, what else are they going to ask you? Okay, the newly infected host can then proceed to infect other hosts, okay, in the same way. You're trying to infect all hosts in a particular high security network by compromising a single host. Of course, a compromised host will be infected with a hopper. So it might be an impossible mission. You realize that you can trick the administrator into installing new direct links between hosts by submitting IT requests. Too many requests may arouse suspicion, suspicion, find the minimum number of IT requests you have to submit to ensure that there exists a single host such that if it's infected with a hopper, then it will propagate to the entire network. Okay, what else are they telling you about this graph? You have up to 500,000 nodes, up to 500,000 edges. Okay. The next M lines contains two integers U and V representing a direct link between host U and V. There's at most one direct link between any pair of hosts, and no host is directly linked to itself. So this is a pretty standard graph setup. And then you have to output a line representing the minimum number of links that you have to add. Okay, you don't have to say where you want to start the infection. Okay, in the first example, there are n equals to 3 hosts. Let's actually just draw it out. So there's 3 hosts and 2 edges. So there's 1 to 2, there's 1 edge, 2 to 3. And if you try to infect 2 first, then nothing else gets infected. If you infect 1 or 3, then the other one gets infected, but 2 is always skipped. So it says that in this network, there's no way to spread the hopper to all hosts by compromising only a single host, blah, blah, blah. But if you submit a request to connect 1 and 3, then infecting any host would allow you to infect everybody else. Right? So you infect this one, that in 2 steps away, it's 3, but actually this will also be infected as well. Okay. And then this other example, apparently you don't need to add anything. It's already it already works. Okay, I don't know if I want to draw this. Well, this is a complete graph. It's 5 vertices, 10 edges, so that's a complete graph of 5 vertices. And I guess it would look kind of like this. 5 choose 2 is 10, so that means all edges are present. And if you start here, then you can, this is 2 steps away, everybody's 2 steps away. So you infect everybody right away. Okay, and then finally, okay, I'm not going to draw this one. This is sort of too many things. Okay, so here that's the problem. Okay, so one of the things that you should realize, I guess, when you read a problem like this, they talk about a graph. So whenever they talk about a graph, you should ask yourself, are there any special properties about this graph that they tell you? And the answer is no. They don't tell you that the graph has a special shape. They don't tell you anything other than the number of nodes and number of edges. And when they don't tell you that, that means anything is possible, pretty much. So in particular, the first thing that I want to say is you could have some nodes that connected in whatever way, and you could have other nodes that are completely separate. Okay, they could be clusters that are completely separated. And of course, these are what we call connected components. And you ask yourself, is this possible that they're separated? And normally they will say, if it's not possible, they'll say from any node, there's always a way to get to any other node or something like that. And they did not say any of such statements. And that means that this is possible. So when you see something like this, immediately you know that there's no way you can infect everybody without adding things. And you must connect these components into something, into a one connected graph. And generally, if you have C connected components, you need C minus 1 edges to connect them. Okay, I'm not worried about whether they can infect each other or not. I'm just saying if you just want to make them into one connected component, you need exactly 3 edges. Okay, so that's the first thing. If you have connected components, you have to worry about how to connect them. Okay, so that's the first thing. So now the next question is, what if you have a connected component? What if you just have one component? What can you say? Right? So if you look at this one, there's no way you can infect anybody and start the infection anywhere and infect everybody. But you know, we saw this one, you can infect something. You can infect everybody. So what's going on? The first thing to realize that is if you don't have, so these graphs here, this one, and this one, if you have no cycle, in other words, if you can't go start somewhere and end up where you started, there's no way you can spread things to everybody. Because if there's no cycle, there's going to be some path, and the immediate neighbor will never be, so you start here, these guys will never be able to be infected because you always have to take 2 steps away. It doesn't matter where you start if you have no cycle. So you have to have a cycle, but what kind of cycle? If you have cycle of length 4 and cycle of length 3, you already know the cycle of length 3 works. Cycle of length 4 doesn't work because you start here and then you infect here, and then you can just keep on going in circle, and you will always be 2 steps away. And you will only be able to infect these 2 and never these ones. And you can generalize odd cycle, you can infect everybody. Okay, so it doesn't really matter how, let's say 7, you start here, then you infect things that are 2 steps away, then 2 steps away, and then 2 steps away, you will be able to infect everybody. You can go around the circle. Whereas if it's an even number, you start here, 2 steps away is here, and then you'll just cycle through these 3. You'll never be able to infect more than these 3. So even cycles are bad. Okay. But even cycle and odd cycle, actually, if you have an even cycle, you can always introduce one edge somewhere. It doesn't really, let's say here, to introduce an odd cycle. And once you have an odd cycle, then the whole thing can be infected, because with this, you can infect these 2. You can infect these ones. And now, basically, if this is distance 0, distance 1, and then distance 2, 3, 4, and so on, this one can go and infect all the ones that are even distances away. These ones can go and infect all the things that are odd distances away, and you'll cover them all. So if you have an even cycle, you can add 1 edge, and you're good. Okay, what if you have no cycles, right? So what if you have no cycles whatsoever? So this is basically a tree. Maybe you have a line like this. Then again, all you have to do actually is add a triangle somewhere. Doesn't really matter where. No, now it's the dog. Now it's the dog that I have to mute. Okay, just a minute. I lost my headphone here. Too many things that I need to mute. Okay, so I add a triangle here. So now this is distance, let's say I start the infection here, distance 0 away. And then distance, these 2, even though they're distance 1, can also get infected because there's a triangle. And now that I cover distance 0 and distance 1, then basically all the even distances can be infected by this one, and all the odd distances can be infected by this one. Okay, so what's the conclusion? The conclusion is that if I have a component that doesn't have an odd cycle, I just add 1 edge, and then I can infect everybody. If I have a component that doesn't have that's an odd cycle, then I don't have to do anything. Now there's some special cases, you always have to ask, did I mislead you, or did you mislead yourself when you do these things? So what if you have a component that is just like this? Yeah, what to do? Is it ever possible to infect everybody? And do we have to worry about it? And then you say, oh, wait, the number of vertices is at least 3. So you can have a component that just have 2, but then you must have another component, another node somewhere. You must have another node somewhere so you can still form this. Okay, so you have to be a little bit careful here, because sometimes you can't just say, oh, there's no odd cycle in this two node here, so just add 1 edge and we're done. That doesn't completely work. So you have to be a little bit careful. Okay, now what happens to multiple components? Right, so let's say I have multiple components, right? I have a tree here, and then I have another tree here. So both of them have no way of infecting everybody. So we said, well, let's add a triangle and then we're done. And then we're done, but we're not done because we still have to connect. So we just connect this and we're done. But it turns out that this is not the optimal, because it turns out that I actually don't need to add this triangle everywhere. I add the triangle on this side and any one component. So if I have a component, I can just add this here. And then from the odd cycle, let's just connect here. So what's happening? Remember I said, let's say I start infecting this one. So this node will go and infect all the things that are even distance away from this initial node. But then these guys are also infected, and it will go and infect all the things that are odd distances away, including the stuff on the other side, because once you connect them, there's no other side. It's just part of your graph anyway. So even though this is odd, so this is now odd, so it will infect this one, right? This would infect these ones, and so on. So in fact, you don't need to introduce this odd cycle in all components. You only need to introduce this odd cycle in one component, and then connect the rest. So what is the solution? Basically, you have to find all the connected components, see if any has odd cycle. If yes, then you just have to basically add number of CC minus 1 edges. Okay, so if you have an odd cycle, then you can just have connect it to all the other components. If no, then you basically have to add 1 edge somewhere to create this cycle, this odd cycle, and then the number of CC minus 1 edges to connect all the components. With with this one special case that you have to worry about it. If everything that you have is like this, if all your components are like this or smaller, right, then you're going to have some problem trying to figure out how to connect them to create this, to create the triangle. But actually, it's not that bad, because even in this case, you're going to connect, let's say, everybody like this. It doesn't really matter how you connect them. So this is now connected. And then you add 1 more edge to create the cycle, the odd cycle. So this formula still works. Does that make sense? Well, there's still 2 problems, right? First problem is figure out the connected components. Second problem is figure out whether a component has an odd cycle. So first, how do you know what the connected components are? Well, there are many ways you can do this, and one way is depth first search. Okay, so that first search, basically you start from some node, pick a node that you haven't visited, you go to all the neighbors recursively. So how do I write this? DFS. Oh, what did Joseph just post it? Okay, hang on.
I just sent you my code if you wanted to show it. I don't know how helpful it will actually be though.
Okay. Well, okay, well, it's not helpful when I put all this writing on top of it. So let me erase that. Hang on, I need to switch my writing tool. So here's the code. Yeah, I don't know how helpful this is. This is DFS. Is it
Yeah.
DFS? But the
Yeah.
problem is nobody other than you and me can, and maybe Josh, can figure out what the hell you're writing.
Well, I thought maybe it would be useful because of the coloring algorithm.
Yeah,
It's-
but the thing is, you use all this funny lambda thing that probably nobody knows what it is, right?
Okay, I suppose that's fair.
Okay, so let me try to explain one way to write that first search. Right? So you have that first search with a function call, and you have a node, and then you say you have some Boolean array that's global, let's say, or you can pass it in if you want. And when you first get into the node, you say visited equals to true, and then for all W being a neighbor of V, if W is, well, I guess switching between pseudocode and English here. If visited, not visited W, then we curse on W. Okay, so this is kind of a standard depth first search. And so basically when you start from a graph, when you call DFS on any node that you haven't visited yet, you will then recursively go and mark all the nodes that are connected to it somehow. So what you can do, instead of using visited equals to true, you could actually have, instead of visited, you can use, I don't know, label. So you can say label, it's equals to a counter, which is the ID of that count, ID of that, let's say the ID of that component. And then if label like this, and I'm just going to kind of on the side set label of, it's an array that's initialized to all zeros. So zeros means you have never seen it. And then on the outside, you would have a loop that goes like this for, I guess, try all the nodes, V0, V less than N, V plus plus. If label, if not label V, then you say DFS V, and then something like counter plus plus. And maybe at the beginning you initialize counter to 1. So the first time through, it will go and mark all the things that connected to V with label 1. The next time, then it come around and look for another vertex that has not been seen, and then it will try to mark all the things that attach to it with counter 2, 3, so on, until you mark everything. And this is standard DFS, and the complexity is the number of nodes plus the number of edges if you use adjacency list. Okay, anyway, we can figure out how many components there are just by looking at the counter at the end. But how do you know if there's an odd cycle? Well, the idea of odd cycle, it's also something called bicoloring or two-colorable. What does it mean? if you have a graph, also bipartite. It turns out that a graph is bipartite if and only if it's no odd cycles. Okay, so what you do? Okay, so let's imagine that you have a graph like this. So of course here I have odd cycles, but you're not going to discover it until later. So you're going to assign, when you visit a node, you're going to assign a color. So black and white. So there's going to be a color that you assign. And I'm just going to use 0 and 1. Okay, so 0 and 1. Assign 0. So you color with 0. And then when you recurse and go to a neighbor, you always switch the color. So when it's the parent is 0, you switch to 1. And then when you recurse on this one, you switch to 0, and so on. Okay, but now here's where the funny part comes in. So you get 0, and then you come down here 1, and then here you get 0. But now it's going to look at this. Of course, it's not going to look at this node because it's already been visited. But if it did, it's going to try to assign a color that's conflicting. And when you see a color that's conflicting, it means that you must have an odd cycle. So what you do is that if you have a node that you already visited, so this is the else part. You say, if my color of V and the color of this node that it's already visited are the same, then I have an odd cycle. Okay, so of course that means I also have to remember the color. Color V equals to, well, I guess this should be capital C instead of U, because now I have too many variables. Color. So I have to pass in the color that I'm trying to use on these nodes. And every time I pass to a neighbor, I always pass the opposite color. Okay. And when I see an edge, so for example, let's say I have an even cycle, just to show you that things will not go wrong. It's going to assign this to 0. It's going to assign this to 1. It come down this way, depth first search. It's going to assign this to 0. It's going to come and assign this to 1. And when it comes back, it says, oh, I have already visited, so I'm not going to recurse. But even though I have already visited, I better check that the colors are different. And if it is, all is fine. But if they are the same, so in this case, right, so 0, 1, 0, and then try to assign these two colors are the same, then I know that I have an odd cycle. So the DFS will help you find the connected components, but it will also help you find whether there's an odd cycle or not at the same time. So this problem is basically an application depth first search, and in two different ways. Both of them, well, actually, I don't know how common it is to talk about that in 3620, but for sure, if you learn depth first search in 3620 or other courses like this, you should be aware of the application to find connected components. And then the bi-coloring or the odd cycles and all those things that may or may not be covered. Maybe it's like a exercise that you have to do. So this is not the most straightforward problem because you need two things. First, you need to understand graphs, right? You need to kind of understand enough about graphs to see what's going on. You have to do a little bit of thinking to figure out what you really care about is odd cycles and then how many connected components there are. And if you can figure that much out, then of course you need to know that you can do it with depth first search. So I actually haven't done that myself, but Joseph has kindly provided his code, which Is there, okay, so how do I, is there a way I can make it bigger or download this or copy? What's the best way? So if I copy this,
I don't actually know. I guess you just copy and paste it into an editor.
yeah. Okay. Uh, no. Okay, I need to copy and paste. So here it is, but now I have to make it bigger, otherwise you can't see. Okay, hang on. Now I have those things hiding. Let me just move this around. Okay, so this is basically adjacency list. A bracket little a, that's the list of neighbors of little a. So you remember that B is a neighbor of A and A is a neighbor of B. This is minus minus because these are one base and he wants to do it 0 base. And then depth first search is this funny thing. So what is this? This C is the color that this is the color that I talk about, the color array. And it's a function, the DFS is a function that takes 2 arguments, the vertex that you're visiting and the color that you're passing. And he's using the color -1 to also indicate that it has not been visited. So it's using the 3 values, -1 to mean that it's not visited, 0 and 1 to mean that it has been colored either by 0 or 1. So, so the main loop, this is basically try all possible nodes. If it has not been visited, call DFS with color 0. And we increment the number of components by 1. Okay, that's pretty much the same code that I wrote, except more cryptic, I guess. Here, this says if the color is less than 0, so if it has not been visited, then set the color to be whatever it is that you're setting it to. Otherwise, if it's visited, then it better be different. Okay, so the way that he checks it is a little bit different than the way that I check it. So the way that I check it is I'm at the parent, and I want to make sure that my neighbors have the different color. But he's actually passing it to going to the neighbor, even if it's visited, and then say, make sure that what I'm trying to give you is what you have already been given. So he checks it at one step further than what I do. So that's why it's Tesla inverted. But anyway, basically, if you have already been assigned a color and you're now being asked to assign a different color, then you're going to remember that in this flag that you have been asked to do something bad. And then here, basically, this just goes through all your neighbors of V, and then recursively call DFS with a different color. Okay, it just flipped a bit. So it's just the same thing that I did with 1 minus C, but he used the hat, but it's essentially the same thing. So the difference is that he doesn't check if something is visited before he recurses. He recurses anyway, but then at the beginning of the recursion, he backs out if it's been visited. So that's slightly different, but it's essentially the same thing. And then at the end, it's just the number of connected components -1 plus 1 if there's no odd cycle. So flag will be true if there's an odd cycle anywhere. So if flag is false, then you need to add 1 more. So this is what this does. Okay, so that's basically the same idea expressed in code. Any questions? Okay, so we're now getting to harder problems, and I think I'm going to stop at the next one, and then I won't look at the bitwise problem. Okay, so how am I gonna do this? Hoppers conveyor belt. This is the one that I want. Okay, so the next problem, this one I've actually done, but it doesn't really matter because I don't think I'm going to show you the code. Okay, so you have a factory with N junctions, and these junctions are connected by M conveyor belts. Each conveyor belt transports any product automatically from one junction to another in exactly 1 minute. And these conveyor belts can only work in one direction. There can be more than one conveyor belt connecting two junctions, and there can be a conveyor belt connecting the junction to itself. So this is a little bit weird, but that's the way it is. The K producers, these are machines that produce products, and they are at the first K junctions, 1 through K. The producer junction J produces a product each minute, X times K plus J for all integers X greater than 0, J equals to blah, blah, blah. Okay, when you see something like this, and if you're not familiar with such things and you want to know, make sure you know what's going on, you have to maybe just try it, just maybe write it out. So let's say, make sure, just get a concrete example. K equals to 3. So that means I have 3 producers, 1, 2, and 3. So it says that it will produce products at these minutes for integers x greater than or equal to 0. So let's try. If x is equal to 0, then this is 0. So at minute 1, junction 1 would producer 1 will produce something. Minute 2, it will produce, second one will produce something. Minute 3, the third one will produce something. X equals to 1, that if you plug in, it'll be basically 1 times 3 plus 1, so it'll be 4, 5, 6. So that basically, if you plug in different values of X, you will see that the number, the minutes at which things get produced would be basically first 3 minutes, the first 3 producers will produce something, and the next 3 minutes they'll produce again, and so on. And they basically take turn every minute. Okay, they go in circle. Every minute it's 1, 2, 3, 1, 2, 3, and so on. So they don't produce things at the same time, but every minute something will get produced by one of these producer. Okay, so that's the first thing to understand, I guess. All products are transported immediately by conveyor belts to the warehouse at junction N, except for those produced at junction N. If any, items produced at junction N are directly delivered to the warehouse, so there's nothing to do. And then you have at each junction, there's a robot deciding which conveyor belts the incoming product should go to, and they can be programmed so that all products produced by producer are always delivered to the warehouse via the same route. Once the robots are programmed, the routing can no longer be changed. Items from different producers may have the same or different routes. And then there are some more things that you have to read, but basically you want to make sure that each conveyor belt only transports at most 1 product at any time. 2 products cannot be on the same conveyor belt at the same time, but there's no limit on the number of products at the junctions. You may turn off 0 or more producers, because sometimes if too many producers are producing, maybe you have some places, maybe some goods that cannot be transported because of congestion, but you still want to maximize the production. So you want to find a maximum number of producers that can be left running such that all the produced products can be delivered to the warehouse, and each conveyor belt transports at most 1 product at any time. Okay, so the first line contains N, K, and M. N is the number of nodes, K is the number of producers, M is the number of edges, and then they tell you all the edges. And then you have to figure out the maximum number of producers you have to turn on. Okay, so let's clear this. So this is very much a graph problem, right? I mean, it pretty much tells you there's a graph problem. You have a bunch of nodes. Okay, a bunch of nodes, they're connected in some way. And then you have some special ones, 1, 2, up to K, that are producers. They produce stuff. And then there are links. Maybe there are links like this. Who knows? And then there's one special one. Maybe like this one. Maybe there's one special one, and which is where everything must be sent to at the end. Now you're told that no edges can carry more than one piece of goods at a time. And so you might say, well, okay, so 1 sends to this, 2 sends to this. So can you actually have both 1 and 2 sending stuff? And you might say at the first glance that no, because if this send 1 here, this send 1 here, you can't both use this one. So you might say, well, no. But there's a catch. The catch is that even though both 1 and 2 produce 1, this produce 1 at time equals to 1. This produce 1 at time equals to 2. So this one can come down here at time equals to 2. And this one can come down here at time equals to 3. And they can, in fact, share the same edge because they are at different times. So that's the little tricky part. So let's imagine, before we get too complicated, let's imagine that there's no element of time here. And let's imagine that everybody just produce something every minute. Everybody produce 1 unit of item every minute. And your question is, how many of these producers can you turn on? So if this is the problem, then this is a very standard network flow problem, where every single node, every single edge would have a capacity of 1. So this would be a capacity. And then you just set up this graph, this is now your sink. You run your standard network flow algorithm. Once you have set up this graph, and whatever the maximum flow comes back to be, that is your answer. Because if you turn on this tap as much as you can, how many units of water can you push through all the way to the sink? Okay, so that's what it is. Any questions in this case, in this simplified case? Now the problem is you don't have this simplified case. You have this problem where the producers are not producing at the same time. So you have to somehow capture this time element. So let's make things simple and just going to do an example and just say that you have only 2 producers, 1 and 2. And let's make things really simple. Like this. We know that the answer is 2. We can turn both of these on, but this graph will not allow us to do this if we just use the same setup. So how are we going to do this? Well, the idea is that you know that this produced something at minute 1, 3, 5, 7, 9, and so on. And this produced something at 2, 4, 6, 8, 10, and so on. And basically things repeat themselves every 2 minutes. So instead of actually just having a node, you actually care about not just what it's traveling on these nodes and edges, but when. And because the cycles are of length 2, you actually only need to know when are things coming into this node, or when are things coming into this node in the odd minutes, and when are things coming into this node at the even minutes. So what we're going to do, we're going to turn this graph into kind of a parallel graph. Let me draw these nodes a little bit bigger so I can, let me get rid of this edge too for now. Okay, so I'm going to draw one, I'll just say odd, odd, and one even. So this is not 0, this is O. And every node I'm going to duplicate into an odd and even parts. So I'm going to expand each node into an odd and even parts. Okay, so I know that at this node here, I can go from this node to this node. But if I'm at the odd time, in 1 minute later, I'm going to be at an even time. And if I'm at even time, I'm going to get to this odd time. And similarly, it's going to set up like this. And you already see, so source, it's going to produce at minute 1, and it's going to produce at minute 2. So there's no production. There's no production here or here. So we don't draw edges here. So in fact, these nodes are kind of dead, but we'll leave them on anyway, just to make things simple. And you'll see that even though here, 1 and 2 kind of get sent to the same node, in this expanded graph, 1 gets sent to this one, and 2 gets sent to this one, so there's no congestion. Because now we kind of separated time. And then here, you can see it's something like this. It sets up like this. And then finally, there's a sink that captures everything. It doesn't matter if it's odd or even. You picked everything up. And if you run max flow on this graph, it will come back as 2, not 1. So what is the point here? The point is that you have to understand that what you care about is not just where things are, but also when things are. You have to know both where and when. And in this case, because I only have 2 things, I only care about odd or even time. And I just connect things in an appropriate way and then run max flow. If I have 3, if k is 3, then I would not just care about odd or even, I would care about whether it's 0, 1, 2, 3. So what does it mean? Time mod 3, basically, because it goes in a circle, 0, 1, 2, 0, 1, 2. And in general, it's going to be 0 to k minus 1, and everything is, I'm looking at time mod k. So I'm going to basically turn every one of these nodes in my original graph into k copies. And then I would have to set up things appropriately, right? So if I have an edge from here to here, then I would be looking at something that has something where it's 1 and then some other time to, let's call this node 3, to 3, and what other time will be t plus 1 mod k. Okay, I will set all of this up, and then eventually I connect all the things that are expanded to the sink into the new sink, and then I can run normal maximum flow, and it will just work. So if I look at this problem, it says that there are at most 300 nodes, and k is at most 300 as well. So basically then, the number of nodes in my new graph is 300 square plus the extra source and sink. So, but anyway, it's basically 300 square, 90,000. And the number of edges is not too big, although in the new graph, you have to set up a lot more edges, but still it's not that bad. Because basically each of the original edges could explode into a little bit more, okay? But it's not that bad. I guess that's all I'm saying. And then you basically run the normal network flow code. So my code is here. So this stuff is just exactly from the code library, the network flow code. I just copy and paste. There's no change here. And then down here, I create a new graph. The number of nodes is the number of nodes times k plus the source and the sink. And then I set up these edges. Basically, for every node that you tell me, I have to set up all the possible j's, and it goes from, I have to come up with a way to index the numbers, right? So I can't just use n comma k like I did with whatever, 3 comma even or odd as a node label. I have to actually come up with a number between 0 to n times k plus 1. Okay, so I have to somehow come up with a scheme, but you can maybe figure that out. So I did it this way. And then I set up the source and the sink to be these two indices, and then I basically just add the edges from the source to the producers, from the last part to the sink. And then after I do all the hard work, I just make this one single call, and whatever answer it gives is the answer. So this is a typical network flow problem where it's not, maybe it's the only problem is to figure out what graph you run network flow on. Once you figure out the graph, then it's trivial if you already have the network flow code. Okay, so this one definitely, I would say, in this region, probably the top 10 teams would, actually maybe that's an overestimate. Let's say the top 5 to 8 teams should be able to solve it, not more than that. I don't think that more than 25% of teams can solve this problem in our region. Anyway, problem perhaps not even top 5. So this is definitely getting up there. And then, okay, I'm not going to talk about bitwise. We were really kind of getting to 9 o'clock. But the other one, well, Joseph did bitwise, and I guess it's probably the top team that would benefit from that discussion anyway. Okay, so this is this one, Singapore 2018. It is a fairly competitive region. Yeah, for those of you that know this book, there's now a volume 4, or the 4th, oh, shoot. Okay, well, anyway, there's a competitive programming book that we use if we actually get to teach 3200, and the author of that book is actually in Singapore running this contest. So anyway, there's now a volume 4, the 4th edition, by the way, for those that are interested. Okay, so that's that for this week. What am I going to do? Let me stop the recording.